start?
Yeah, go ahead.
So, good morning, everyone. Today I present this paper from Nature Method, and we will cover deep interpolation. Sorry. 잠시만요. 뭐가 떠가지고. I think it is really helpful for who want to denoise their image. As you know, neural signals such as calcium imaging and voltage imaging are weak to potential noise, and this noise is unavoidable and can decrease downstream analysis. And as shown here, the ground truth and the low image can see well due to noise. And so traditional denoising methods such as Gaussian and median filter couldn't make images clear, but denoising methods can be deferred to the domain data. And previous research like noise void or any self-supervised learning just consider a 2D single image, not a temporal image, like classroom imaging. So this paper want to consider spatio-temporal image. At our last lab meeting, I introduced lowest void. Maybe you guys remember it. It masks the center pixel and predict it from neighbor pixel. So it only see the single image spatial information. And in contrast, deep interpolation masks the frame and predict this frame from the number of neighbor frames. So by using these multiple frames, you can see the spatial and temporal information. So how can it denoise? The key idea is the neighbor frame share the same signals such as structure or event, while their pixel noise independent from one another. And if you don't use the target frame itself and instead predict from its neighbors. So here the target frame T is only from the input, and only the neighbor multiple frames are provided to the model, and the model is trained to infer T from the spatio-temporal patterns. And after training, the model reconstructs the target frame T from its neighbors. It looks like the frames are the same, but if you look at the residuals with the target and neighbor frames, you can see the difference like this. From the residuals, neighbors share the same underlying structure, while the noise patterns change from frame to frame like this. In other words, pixel noise is independent across frames, and this is our key assumption: same signal and independent noise. And then we average k neighbors like this. So signal could be remain, but independent noise will be zero in expectation. As a result, you can see that the observed frame YT eventually becomes defined only the true signal ST. And since the random noise averages out and disappears like this. In other words, by averaging across multiple neighbor frames, the independent noise cancel out, leaving us with a only clean reconstruction of the underlying structure. Any question
John,
from?
John, could you explain? Okay, could you explain that part again? I think that's important, right? Could you explain how you
어,
get the clean signal one more time?
sorry,
Uh, could you
질문이,
explain this one more time?
아, 어디부터
아,
설명해야
아까
될까요?
그거 캔슬한 것부터.
아,
이거.
um, they use the number of neighbor frames to make a target frame. So they they average the K and
So
just
how do you determine the K?
you mean the define K?
Yeah, define K.
K is the number of frame. So they use the just 30 frames.
I see. Okay.
K means seems like input, number
Gotcha.
of input. And
How about
this
neighbors? How do you define number of neighbors?
um they just describe the time gap in the frame, but I forgot it already.
Okay.
Yeah.
But of course, they have to specify number, the send number, right? Or they have a formula for it.
Yes.
정해진 거야? 그러니까 그치? 정해진 거야? 아니면 이거를 계산해낸 거야? 그러니까 네이버를 계산해야 돼? 아니면 네이버는 정해진 거야?
네이버는 정해져 있습니다.
어떻게 보면, you know, don't you have to calculate the neighbor? Based on the noise? Of course, you don't know the noise, but 그러니까 그냥 set 그냥 how do you optimize it then? How do you optimize the number of neighbors?
This is the loss function to
hmm
optimize.
hmm
So y and left one is the previous time frame, and this is after time frame. So input this and then make a target t like this, and they want to uh, they want to decrease the loss value.
Okay, I understand that. Okay, but how do you uh, okay, they just use this continuously one by one. The move on frame by frame, or they use a number of like a set of frames.
Yes,
They use a set of frames, right?
yes.
Yeah, okay, and then you don't know how they determine the set, or you know
Determine
the number of sets.
30.
No, 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 no. 셋 안에 드는 게 몇 개, 프레임 몇 개 들어가냐고.
아,
음.
그 they try the various data sets, so I don't know where because different with the data set.
Yeah, so that's my question actually. That's right there. So they use a variable number of
Ah,
sets to optimize, right?
yes.
Is there any way to calculate that number before just randomly trying? That's my question. Okay, that's it.
Um,
Because you have to run. I mean, every time you have to, do various number of frames per set. It would take so much time to optimize it, right?
yes.
Yeah. So is there any when you want to optimize beforehand before you run it?
But I
But
think that it just use the K neighbor frames, so I think that the number of the all data frame is not important in my opinion because
number.
they use the just K input image.
Okay. All right. Okay. Okay. Yeah, we can talk later about this, but I think that defining these numbers, I think it's important. I think. Of course, who knows about AI, right?
Yeah. Can I skip?
Yeah, sure. Of course. Done.
So in classroom image, they use a 2D convolution encoder decoder with skip connection similar to a unit style. The task is the predict the target frame by using several neighbor frames before and after it. By learning from these neighbor frames, the model can fill in the missing one using only nearby temporal information. For electrophysiological recording such as EEG and MEA, they extend the same concept, but just using the 1D convolution. 1D convolutional means not the image, just using the signals. So this allows the model to interpolate neural signals over time and capturing temporal correlation while filtering out noise. I think this idea is will be helpful for our MEA project, so I will try this one later. And for fMRI data, they use a 3D convolution network. And the network predict the missing 3D blocks such as brain volumes. And here is the result. I think in AI paper, the method is more important than the result, so I just explain briefly. And as you can see, the boundaries of the cells are clear and the most of the noise has disappeared like this. And the light graph showed that the model didn't distort and hallucinate any signals, and it only removed the noise while preserving the structure. And finally, the bottom graph show the single pixel SNR distribution, and easily this means interpolation makes the SNR more higher. And oh, hold on. Sorry. And this is the electrophysiological recordings result. And as you can see, the original and deep interpolation. And this is the um, number of the channel, and it's the time. And their input is the signal. So as you can see, the noise will be disappear a little bit, and while preserving the signal's shape. And the fMRI, comparing to low and deep interpolation, they preserve the structure while the independent noise will disappear. And this is the residuals. Residuals indicate uh, independent noise. So model remove this one to make this. And this is conclusion. And deep interpolation is self-supervised model, but I think this benefit is for the time frame, like a custom image, not a single image. So I think this is the important idea to this paper. And thank you for listening.
시연아, 아까 다시 한번 그 컨클루전만 볼래? 다시 컨클루전. So again, just for everyone, and maybe I misunderstood. There's a plus minus n neighbors, right?
Yes.
What's this? What's the n? How do you determine n?
And
N n plus minus n neighbors, right?
ah,
N
ah, ah.
A B C D.
Um so I think the coding is the also experiment, I think. But so the n is not defined value. So they try number of a different value of the n, but
Okay.
they just get the result. 30 is more better than other n.
I'm better than 60?
So, um yes, 60.
Oh, no, it's 30 was better than 60. I mean, let's say more isn't wasn't more the better or
Yes, more the better.
So
The
60,
optimized optimized result.
너, 시연아, 60개를 쓰면 더 좋아? 그럼 30개보다? 결과가?
네, 맞습니다.
So that doesn't mean anything then. What I'm saying is like, is I think, boy, I mean, it could be right, but then all at the same time, it sounds a little
Um,
odd because you have to get all the as and the more numbers will just eventually arrive at uh, and it was you were talking about the spatial temporal, right?
yes.
But if you increase more numbers, wouldn't it push towards spatial rather than temporal? 그러니까 더 스페셜 강조되지 않냐고. 뭐 하나가 더 강조되지 않냐고. Let's say, maybe temporal is 어떻게 하면 temporal이 더 강조되든지 스페셜 강조되든지 그런 게 보이지 않을까? Depends on how you.
n이
음.
늘어갈수록 템포럴이 더 늘어난다고 생각합니다.
temporal 늘어나는데
Oh,
네네.
so let me,
아웃풋이
yeah. I don't think we have enough time. So I put some of the comments on this choice of K and the duration. I don't agree with the Xian that the more number of N will give a better results
yeah,
because
okay.
this we are actually using spatial temporal, especially temporal information here is based on the characteristics of, in this case, calcium imaging transient. So just the longer, I think Hyojung also kind of asked a question whether that may like smoothen the actual signal. So I guess the number 30 is not the most important. In that paper, they actually did try the various durations, but the important part is the actual biological signal, the decay kinetics of GCamp 6 fluorescence. And they have done kind of training and validation using their computation. So I think this is an important issue and important probably key parameter when you use this. I was also curious about whether this is only for calcium imaging, but they use mostly calcium here, but it can be applicable to voltage imaging. I guess that's probably future task, what the paper actually claimed. But at this point, I think we have to stop because we have another meeting ensuing. But yeah, thank you, Xian. I think this is very interesting one. And all there are a number of questions. Xian, could you please copy all these comments and use the select to answer even later?
Yes, professor.
Okay. Yeah. Thank you, everyone. And I think I'm gonna take picture again. Final. All right. Smile. 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 All right. I think those two papers are absolutely very interesting. I'll be also sharing the content later. All right.
야, 승준아, 너 이름 바꿔. 임정묘 알지? 임정묘. 어? 너 정면어?
네, 죄송합니다.
오케이.
Mm. All right. I'll see you guys around.
Alright. 바이바이.
Bye.
너 봤어, 영승? 저 자식 저거.
왜? 영승이 왜?
저 새끼 주먹 감자를 날리고 있어, 뒤에서 저 새끼.
자,
이거 일로 들어오는 거 어떻게 된 거야?